We use the sigma summation notation to, find the area by, partitioning the given interval into subintervals, and we approximate, um, you know, we approximate the area under the curve by, adding all the rectangles area, right? So there are two different, approaches you could, apply. One is called, underestimation. Another one is lower estimation, right? Okay, so before going to look at that, these are the basic, the geometric formulas, you could use with summation notation. Okay, do you understand this notation?
Yes, sir. Yeah, I finally understood it after a while.
Okay, so if you, have the variable here I, that means I running from 1 to n. So you are repeatedly n times, adding, some number. Since c is constant, remember I from 1 to n of constant means you could pull that constant outside, and you could write, you are running I from 1 to n with the constant 1. That means, you are adding 1 n times. So if you count this, there are n of 1s, right? That is simply n. That's why answer is c times n. So once you have constant, the summation I from 1 to n is that constant times n. But the second one says, this is rule number one. Rule number two says if you run, and in another word, the summation for n times of I, that means what? This is nothing but if I1, you will get the first term, which is 1. Then you are adding the second term, I running from 1 to 2. Next to I is 2. The next one is 3, and so on, right? So the last I value is going to be n. So you are adding this all. Formula says that, simply 1 to n, if we add all the numbers, that is simply n by 2 times n plus 1. This kind of formula you could think of, right? The third formula says that if you want to add again I from 1 to n of I squared, that means what? If I is 1, you will get 1 squared. Plus if I is 2, you will get 2 squared, 3 squared, and so on, up to that. The last term is going to be when you're plugging I for, n, you will get n squared. Formula says that if you add these from 1 squared to all the way n squared, which is n over 6 times n plus 1 times 2n plus 1, right? And the last formula you see again, I from 1 to n, but you are adding now cube of the number. This is 1 cube, 2 cube, 3 cube, and so on up to n cube. So this is simply formula says n squared times n plus 1 squared over 4. So you could apply this basic formula to find the summation of the given problem. Okay. So look at this example. Evaluate this summation for different cases. The first case say that assume n as 10. Okay. So before going to find these, so you could simplify this by using these properties. Okay. So how can I simplify? This could be simplified like this, right? Remember, I is the only one varying from 1 to n. You could think of n as a fixed number, like a constant. Only I is the variable here. So if you have constant inside the summation notation, you could pull out. Okay. That's why here, if you look at this step, right, this n squared is now pulled out, and that is 1 over n squared. The remaining I plus 1 is inside. Now again, if you have plus sign in between two numbers with the summation, you could distribute the summation term by term. Okay. So this is nothing but equivalent to summation I plus summation of 1. Okay. Now you could apply those results. Remember, summation I from 1 to n is n over 2 into n plus 1. So if you plug in that here, but summation, as I said earlier, summation 1 from n I from 1 to n is simply n. So now use some algebra and simplify this. Okay, find the common denominator and multiply and simplify. You will get that. Then again, you could simplify further. Here you could cancel 1n and here 1n and you will get that. Okay, so the given problem now is reduced to this, right? So the given problem, this guy is now reduced to that. Remember, in my answer, there is no more summation notation because I applied all the formula for the summation, right? Okay, now you consider case by case. The first case you need to find for, the summation n is 10. That means what? Simply if you plug in 10, you will find out the answer. That is the summation I from 1 to 10 of I plus 1 over 10 squared should be simply plugging here 10. 10 plus 3 over 2 times 10. Okay, so that is 13 over 20. So this is the formula we use now, right, for that. What does mean by that? That means if you find the sum of this, you should get 13 over 20. Okay, so if I is 1, you will get 1 plus 1, which is 2 over 10 squared, plus if I is 2, you will get 2 plus 1, which is 3 over 10 squared, plus 4 over 10 squared, and all the way up to when I is 10, you will get the last term, which is 10 plus 1, which is 11 over 10 squared. So this is the explanation of the summation notation in the left side. Okay. If you are asked to simplify this is not an easy task, right? You have to type one by one in your calculator. But if you check after typing this, you will come with this answer. You see now, formula will give you kind of shortcut to find out the summation, right? Suppose if you have here 100, it is not easy to, use the calculator here because we have to add 100 times. That's what this formula is always effective, okay? So simply I have explained here how to add up to 10 terms. So a similar formula can be applied for 100 terms and 1,000 and 10,000 terms, okay? So these all kind of getting idea about the summation notation before getting into the real problem, okay? Okay, what is our task? Our task is to find, the area of the curve. So look at this problem. Use 5 rectangles to approximate the area of this curve with the x-axis between 0 to 2. So 0 is here, 10 over 5 is 2, right? So you are asked to simplify finding the area of this, right? So how many rectangles you need to take? You need to take 5 rectangles, okay? So that means what? That means you have to find one by one the area of each rectangle, okay? The thing is here, how are we going to find the area of the rectangle? Remember, to find the area of the rectangle, you should know the length of the rectangle and the height, right? So I need to know two things for each rectangle, okay? The length of the rectangle is nothing but the length of this interval, right? So if you want to find the area of 5 rectangles, that means you have to divide the given interval into 5 subintervals, okay? Remember, you are asked to find the area between 0 to 2. So that means your x value starting 0 and all the way up to 2, right? Now you need to divide this entire interval into 5 sub-intervals. Okay. So how do you find the, the interval width of the small interval? That is simply given by this value, subtract the left value, then divide by the number of rectangles you wanted. I want 5 rectangles, so you have to divide by 5. So this will give you the length of each subinterval, right? This is 2 over 5. Okay, that means if I mark here 2 over 5, so like that I could find 5, rectangles. 1, 2, 3, 4, 5. So let me draw with the equal, right? So each length is now, the interval length is 2 over 5. So this is 2 over 5, this should be 4 over 5, this is 6 over 5, this is 8 over 5, and this should be 10 over 5, which is 2, right? So like that, we have divided into 5 sub-intervals, right? Okay, so you know now the length of the rectangle. Then how do you find the height of the rectangle? Height of the rectangle is nothing but the function value, right? There are two ways you could find out the height of the rectangle. So if you want to, find the underestimate here. So if you look at the picture, what we have done is here we have taken which endpoints. We have taken right endpoints to each interval, right? For this interval, I have picked the right point and to find the, draw a vertical line all the way up to the curve. So this is going to be the height of the rectangle. So again, take the second, rectangle. Now for the height of the second rectangle is up to here. So basically for each rectangle, you have to find the function value at the particular x value, right? Okay, that is why when you add all, so you will get, you know, you will get for ith rectangle, right? I could be any number from, I could be any number from 1 to 5, okay, because I have up to 5 rectangles. So arbitrarily, I'm talking about ith rectangle, right? So if you look at the ith rectangle, what does mean by that? That means, so you could find, the ith rectangle will be like this, okay? Remember the class width for each rectangle is same, which is 2 over 5. No change in the length, but height will be changing, right? Okay. So now you remember for first rectangle, right end point is 2 over 5. Second rectangle, this is right end point, which is 2 times so 2 over 5, which is 4 over 5. In similar way, you know, the right end points of my ith rectangle is going to be 2 times, I times 2 over 5. That is 2i over 5, right? So if you're plugging I is 2, you will get the second, second rectangle's height. So this is basically, um, the right end point of ith rectangle. Okay. So then if you're dividing the subintervals, 1, 2, 3, 4, 5 subintervals, we keep all the right endpoints for each interval. So remember, this is my first rectangle, second, third, and so on. So simply we use the formula now, right? So this is nothing but the area of ith rectangle. Since I have 5 rectangles, so you have to add one by one. So that is, in summation notation, I from 1 to 5. So this is going to be my height of the ith rectangle. Remember, height is given by the function value. Take the given function, evaluate it, at the right endpoints. Okay, so we are picking the right endpoints. Then multiply by its interval width. So you will be given function. For this problem, what was my function? Function was negative x squared plus 5 minus x squared plus 5. So simply plugging this is my now x value. Simply plugging this value into your function. Remember, my function was negative what? Negative x squared plus 5. Okay. So function was negative x squared plus 5, but I need now, I need f of 2i over 5. So simply plugging x for 2i over 5. So that means this will be 2i over 5, but I have squared here plus 5, right? That is why you have this step. Then use some algebra and simplify. So if you simplify, let us simplify this. How do you simplify? Square them. 2 squared is 4, I squared over, 5 squared is 25, okay, then plus 5, right? So could you simplify further? Okay, let me write down this as my function value. So remember, your task is to find this one, right? Summation I from 1 to 5, function evaluated at 2i over 5 times the interval with 2 over 5. So now I have simplified this piece that is here. Okay, so I'm replacing this guy, negative 4 over 5, 25 times I squared. This is my, you know, this is my f of 2 over 5. Remember, you have 2 over 5 outside of function multiply. So now simplify this guy. You know now summation properties, right? 2 over 5 is constant. You could pull in front of the summation and you could distribute the summation separately. So you will get that as, I from 1 to 5, negative 4 over 25 constant, again I squared, then plus I from 1 to 5 of this constant 5, right? Okay. Then we use the formula for this guy. Okay. How do you find this one? Sharon, tell me, how do you find this? Hello, Sharon. Are you there?
Yes, sir.
Okay.
Wouldn't that be just doing like the third formula, summation formula?
Yes. You know now n is 5 here, right?
Right.
Okay. So use the, third formula, plugging 5 here, and you will get that. Okay. And so that is 2 over 5, negative 4 over 25. So if we use the third formula with n is 5, so you will get n is 5, 5 over 6, n plus 1 times 2n plus 1. I'm simply using the third formula, right? Then plus, this is nothing but 5 is constant. I from 1 to 5 is simply 5, right? So that is it's 5 and 1, 5 I could cancel, right? And this is 2, this is 3. So you will get negative 2 third here. And here you will get 6, 5 plus 1 is 6. Times here you will get 11, right? Plus here you will get 25. Now simplify this, you will get that answer. Okay, will you get? Let me check. 2. So 2 times 2, 4, 4, negative 44 plus 25. Okay, n over 6 and plus 1 into 2 n plus 1 plus here you get 25. Yes, correct. So I could divide by 5 here and here. So negative 2. Oh, I missed this 5, right? So that is negative 44 over 5. So now this is 2 over 5, negative 44 plus 125 over 5. That is 2 over 25 times 125 over 25. Yeah, that is how much this is. Subtracting 44. So you will get 56. It's 81, right? Yeah, 162 over 25. So that is the area of 5 rectangles. So you have so many, steps to finish this problem. Only thing is you should know how to apply that summation, things. Get practice. Okay. So this all about by taking the right endpoints of the subinterval, right? So to find the area with the left endpoints, do the same steps. But for the left hand points, now, remember my left hand point start with 0. So in such a way, you have to, adjust this ith formula, right? Remember, I is my, the number of rectangle here. So I should start from 1 all the way. So if plugging 1 here, you should get the left hand point. So the first left hand point is 0. So you have to get here 0 when you're plugging I, that is why we adjust our formula according to that. Okay. So then do the same procedure and find the left area. Left area and right area may be having a different answers, right? No need to have the same answer. So here you got 8.08, here we got 6.48, two different answers, doesn't matter. So this is the way to use, um, the summation notation to find the area that is there. But now you could use the limit definition to find the area. Okay, this is the most important thing we wanted at this, section. Definition of the given area of the region by using the limit summation formula. So this is the important formula. We have to use this. Okay. You will be given a function, right? So you need to find the area between 2 points. So here delta x is nothing but the length of each subinterval. Remember, we divide the given interval into equal pieces. Therefore, each subinterval, has same length. That length is the delta x. Okay, right? So what are you doing here? You are finding the function value like earlier, finding the area of the rectangle. But now here you are chopping up into n subintervals, right? After finding the area in terms of n, we let the n go to infinity to find the very, very good approximation area. So we use this formula. So if you are asked to find the area with the limit definition, you have to use this formula. So I have included some problems for coming test, so you could look at practice test. And have you gone through the practice test?
Yes, sir, I have.
Yeah, so I have included a couple of problems. These I'm working on now our practice test. Hopefully I will post a solution tomorrow evening, I think. Then you could work on this problem. Okay, so you have more work to find this. Look at this. Let me explain this problem. Find the area of the given region bounded by the graph of x cube, x-axis, and the vertical lines, x is 0 line and x is 1 line. Okay, so this is the area you need to find out. Okay, this area we need to find out, but we are going to use the limit definition. So you have to understand the question carefully. So if you are asked to use the limit definition to find the area, you have to use that formula. Okay, so area is given by limit n goes to infinity of the summation I is running from 1 to n of the given function evaluated at any point ci times delta x. Understand carefully what is the ci. Ci is nothing but a point inside your subinterval. Okay, suppose if this is your ith subinterval, ci is the point anywhere in this closed subinterval. Okay, you are free to choose any value of ci, right? In most of the cases, we pick ci as either left-hand point or right-hand point. It's up to you. You could choose either one as ci. Okay, so look at this problem. What did they have done here? So basically we are finding this area, right? So the given interval is now 0 to 1. So that is the given interval, 0 to 1. Okay. What is our task? Our task is to divide this entire interval into little n intervals, subintervals. So you need to divide n subintervals here. Okay. So how do you find the length of each interval? Simply that is denoted by delta x, which is formula says that b minus a over n. So what is a and b here? A and b simply are the endpoints of the given closed intervals, right? So in this case, a is 0 and b is 1. So then what is that? That is 1 minus 0 over n. That is simply 1 over n. So this is going to be our, the subinterval length. So now you have to pick the CI. Okay, let's look at this work. So what are they telling here? Yes, the length of the subinterval is 1 over n. We have found that already. Okay, if this is the case, remember this is my given, the interval. Sorry, that should be 1. 0 to 1. Now, if you take the first subinterval, you see now the length is 1 over n, right? So this length should be 1 over n. If length is 1 over n, you are starting with 0. So this point should be 1 over n then, right? The next point should be 2 over n, 3 over n, and so on, right? So the last n point should be n over n, which is 1. So if you look at here, in between this point to there, you will have little n of subintervals, right? Okay. Now here, what are they doing? They are taking CI. Remember in my formula, where's my formula? This is my formula, right? I told you CI is the point inside the closed interval. You could take endpoints as well. Okay. So here they are choosing CI as a right endpoint. Okay. They're choosing CI as this right endpoints for each subinterval. All right. That means if you look at somewhere here ith subinterval, the right endpoint is going to be I over n, right? Because for the first interval, right endpoint is 1 over n. For the second interval, 2 over n. Third is 3 over n. For ith, I over n. Okay, so they choose CI as I over n, right endpoint. It's up to you. Okay, one more time I'm telling you. You could choose left hand points as well. So CI is now I over n. So simply apply this formula to find the area. Limit n goes to infinity of I running from 1 to n. Okay, remember the given function fx was x cubed. So you need to find now f of ci, simply plugging ci in place of x. So you will get ci cube, right? Remember, I have chosen ci as my right endpoint, which is I over n. So simply take the cube of that. That is why you have here I over n cube times, the interval of length of the subinterval, so which is 1 over n. So now do some algebra and simplify that. So that is simply I cube over n cube over n is n4. So n4, remember n is fixed number, so you could treat like a constant. So pulling outside of the summation, only I is the variable running from 1 to n. Okay. So now we know how to find this guy by using the summation properties, formula number 4, I believe. So if you apply that, the summation I from 1 to n of I cube is n squared times n plus 1 squared over 4. That's it. Now we already have studied limit. Simply find the limit of this function, n goes to infinity. What will happen? If n goes to infinity, 1 over infinity is 0. This is going to be 0. This is going to be 0. Only constant part will be, that is 1 over 4. So the area is 1 over 4. You have more work, if you are asked to use the limit definition. We had the same situation when you study, differentiation, right? There also, we worked finding derivatives by using limit definition. You had more work. Similar way you could think of here for the antiderivative problems as well. Okay, so keep in mind, if you want to find area by using limits, you have more work. Like this, you have to do the problem, okay? That makes sense?
Yes, sir.
Okay. So you could work on this problem as well, the same procedure, and try to understand. So that is there in 4.2. Okay, now for the 4.3, the same notion we continue, but we give one special name of those procedure, which is called the Riemann sum. Okay, So the Riemann sum is nothing but, mm, the one we're working out here, the limit definition things, it is called the Riemann sum. Okay. So just go ahead and read these things. Okay. So the Riemann sum is nothing but we have the summation with the limit. So this guy is Riemann sum. Okay. So now how are we going to connect Riemann sum with the integral, antiderivative? So whatever we find the area, okay, this guy is equivalent to write down limit n goes to infinity of the formula earlier we had the area, the same notion, okay? Okay. So now remember here in the Riemann sum, we have here, the length of the interval may be different for each, but normally we keep this as the constant value. That is why you have delta x there in the previous formula, right? We fix this guy. We fix this guy throughout the, subintervals. That means what? That means we have equal length of, the subintervals. That is very convenient to work on, okay? So hereafter, the connection is now, this is the Riemann sum is nothing but the area of the curve or the antiderivative of fx from a to b. Now we are slightly moving and, we have this result. What is that? The area of the curve, the area of any curve from a to b, say this is the given curve f, the area of the curve between a to b, right, is simply now given by the integral formula a to b of fx dx. Only the condition is your function should be continuous and non-negative. Non-negative should be above the x-axis, on that closed interval. Then area is given by this antiderivative formula. Remember, in 4.1 at the beginning, we had a list of antiderivative formulas. So you could use those formulas to find the integral of, the given function. Okay. So now this is all the explanation. Now you know, right? So the antiderivative for the non-negative function means nothing but the area of the curve, right? So the first explanation, this guy, the integral of 4 from 1 to 3 is nothing but this is your function. Fx is now 4, right? Y is equal 4 line. Sorry, y is equal 4 line from 1 to 3. So you are simply finding the area that is given by this formula, right? So you know how to find the rectangle area. So length is 2 and height is 4, 2 times 4, which is 8. Therefore, the area, the integral answer is 8. Okay. So if you look at the second picture, okay, x plus 2 is the straight line. So you are finding the area from 0 to 3. So that is nothing but, you see, this, the colored area is nothing but the trapezoid, trapezoidal area, right? Shape is like a trapezium. So we know how to find the area of trapezium, right? So that is the sum of the parallel side and divide by half, then, and its height. So you know the formula of the trapezoid, right? So simply use that formula and you will find that. Okay. So the third one, again, it is a semicircle, negative 2 to 2. So we know how to find the area of the half circle. So simply that will give that. So this is nothing but the relationship between the antiderivative and the area of, the given curve. Okay. So again, we have some, the additive properties for the definite integrals. We call definite integrals once you have the limits. We call those two as the limits, right? If you see some number here and there, we call that as a definite integral. If you do not see any number, which is called indefinite integral. Okay. So you could use those properties as well to find out the antiderivative. Okay. So now here we use those properties to find the area. So you know now how to use. So if you have plus sign in between, so you could split the integral sign and find like differentiation, right? So you could find the integral for term by term, the first term integral plus second term integral and third term integral. Then you know how to find the area. So um, just use those and find the answer. So you can go through these things. And of course, you were asking about 4.4 and 4.5 today, right, Sarah?
Yes, sir. The schedule said we were supposed to have a quiz today.
Oh yeah, I just postponed it quick to the next week because I just thought that you want more time to study.
Yes, I would.
Yeah, that's what I just skipped that into next week. Okay.
Okay.
Right. So 4.4 is nothing but the continuation of the the antiderivatives. Now we have kind of concrete formula to find the definite integrals. Okay, that is called the fundamental theorem of calculus one. Calculus. This is you could treat like the fundamental theorem of calculus, theorem number one. You could think of. Okay, so this is very useful formula. If you are asked to find, definite integral, for example, if you want to find the integral of x squared from 1 to 3, right? So in this my example, f is x squared, a is 1, b is 3. How do you find this answer? Simplify, you could go through 4.1, the antiderivative formula we have, the list of formula. So there you will find one formula to find out the power, right? So what is the antiderivative of x to the n? Do you remember? What is that? The antiderivative of x to the n. Go back and check 4.1. Like derivatives, here also you have the power rules for antiderivative, right? Yeah,
You add 1 to the exponent, and then you
exactly.
add, and then the bottom is 1 plus the exponent.
Exactly. So you need to divide. So this is equals, x to the n plus 1 over n plus 1, right? Okay, remember I told you there, if the given problem is little f, if this is little f, we denote antiderivative answer as big fx. Do you remember? So find the antiderivative answer for the given problem, okay? Then plugging these two values, we call this as upper bound and the bottom one is the lower bound, okay? First, find the antiderivative of x squared. So if little fx is x squared, then remember according to our notation, big fx is nothing but the antiderivative of fx, little fx. So formula says that the antiderivative of x squared is x3 over 3. Okay, so this is the way to find out. So find the antiderivative of inside function x3 over 3. Okay, then we put like this one stroke if you want. You put this like notation we use. Now put the bounds whatever you have. Formula says that that should be equals to f evaluated at the upper bound, right? Remember our function f is nothing but now the antiderivative function, right? Simply plugging that upper bound value into that function. Now this is my fx. So f of b means here nothing but, remember our a is here 1 and the b is 3. So you need to find f of 3. This is my f of b. And f of a is f of 1. So you have to find these two guys, then subtract them, right? In another word, I'm asking you to evaluate the answer, the antiderivative answer at the upper bound point. That is simply plugging 3 into that function. So that is 3 over 3. Then subtract, again, plugging the lower bound of the given problem into your antiderivative. The lower bound is 1. Now plugging 1 into your function. Your function answer is here, right? So 2 times you had to plugging the values with the same function here. Now you will get 2 numbers. Just simplify. That is going to be your answer. So that is 3 to the power 3 over 3 is 9 minus 1 cube is 1, which is 1 over 3. So answer is 9 minus 1 over 3. Okay. So that is the way to find out the answer for the definite integrals by using the fundamental theorem of calculus, the theorem number 1. You see now, we use that notation, right? Let me repeat. What are the steps you are going to follow? So simply find out the antiderivative of inside function, then use this notation. You could use either, um, right side square bracket or just simply stroke a straight line like I am using here. You could use either notation. Then copy down those 2 bounds. After that, take the upper bounds first, plugging into the function, then subtract the lower bound, plugging into the function like this, okay? Remember here, in this problem, they have x cube. So the antiderivative of x cube is x4 over 4. Then copy down these 2 bounds, then plugging the upper bound first to x, then subtract the lower bound. That's it. That makes sense? So when you have the bounds in the problem, we call that as definite integrals. But for the definite integrals, you don't need to put that arbitrary constant, okay? This arbitrary constant we plugging only for the indefinite integral. If you do not see any number here and there, then put the arbitrary constant. If you see the bounds, you don't need to put arbitrary constant. That is why I'm simply using the function itself without C. That's what they mean here. It is not necessary to include the constant of integration C in the antiderivative. Does that make sense?
Yes, sir.
Yes. Okay. So again, if you have plus minus sign inside the problem, you could split into 2 pieces. Okay. So I'm using the integral property. So this is -1 to 3. My first function is simply 4 dx. Then subtract again -1 to 3. Second function is x squared. So you could rewrite like this. Okay. Remember I told you last time, if you have constant inside the integral, answer the antiderivative of constant is that constant times the variable, now variable x. So that is the antiderivative of 4, right? 4x. Now plugging the limit 1 to 3. Then I see the negative sign. Now find the antiderivative of x squared, which is x3 over 3. Now plugging the upper bound, lower bound like this. Now, as I said earlier, plugging first upper bound into your variable x, that is 4 times 3, then subtract the lower bound plugging value, that is 4 times -1. Then come to this point, then negative. I have here 3 upper bounds. Oh, so you have to be careful here. This negative is common. Open the parenthesis, then evaluate this, okay? When you have minus sign here, you have to put the parenthesis. Otherwise, you will have a minus mistake. Now plugging the upper limit here, 3 over 3. Then always subtract the lower. Lower bound has now negative sign over 3. That's it. Now you have to simplify. 4 times 3 is 12. Minus into minus plus 4. Then minus, let us simplify inside first. This is 9. Right? -1 cube is -1. And this is positive 1 over 3. Then that is 12 plus 4 is 16 minus. Now you could distribute the negative sign outside. So 16 minus 9 is 7 minus 1 over 3. Okay, so that is 21 minus 20 over 3. So, but here, if you look at here, the same procedure, right? But they are plugging the limit all together. You could do that all as well. You could apply, the bounds all together or separately. I just here use separately for these 2 functions, okay? Because that is easy. If you want, you could plug in directly as well. Doesn't matter. Okay. So now remember At the end of this course, Cal 1, our task is to find like these problems, finding integration with limits. So we are almost there. So the fundamental theorem of calculus, the second version is nothing but, remember I explained this earlier. Remember, this is nothing but the antiderivative answer of ft evaluated from a to x, right? Remember, a is constant here, x is variable you could think of. That means this antiderivative answer after evaluating the bounds will have function in terms of, x, right? Once you have the derivative of that answer, you should get back to the inside function, right? In terms of x. What do they mean? They mean simply if you see the constant value here and the variable there, answer is the derivative of the integration is nothing but the inside function. In place of t, simply replaced by x. Okay, so that's very easy. So you could use the second fundamental theorem of calculus for the continuous function, right? So if you apply that theorem here, remember the given integral with the variable t, but after finding the antiderivative of this function, you will get the function in terms of, t, right? Then you will plug in the limits 0 and x. After plugging the limit, you will get the ultimate answer in terms of x, right? Because you are plugging the value x here. Once you take the derivative of that, you have to get the inside function, but replacing t by x. That is why you have this. The same answer, copy down that here, but switching the variable t to x. Okay, so this could be done only for a continuous function, yes. So I believe you could go through those things and so many formulas we have here. Okay, so the last point today, I'm going to, summarize this, the substitution rule. So the substitution rule is nothing but one kind of technique, one kind of technique to find the integral problem, okay? There may be some, the complicated function inside the integral. So then we use this technique to, do the given problem, okay? Okay, what does mean by that? That means, so if you see this kind of pattern in the given problem, you are given a function and then its derivatives here, then that could rewrite in this form. Okay. Now look at this example. You are given function like this, one function times another function, right? So if you look at carefully, if you let g function as x squared plus 1, right? That means you could rewrite this problem as g function squared times g prime x dx, right? Because if my g function is x squared plus 1, then the derivative of g function, which is g prime, is 2x. That is right over here, right? So if you see one function here and its derivative here, we call this all kind of pattern. Okay. So if you see this pattern always, you could rewrite this guy, simply use that gx as some other variable, say u. So if you see this pattern, some function with g and its derivative, so simply, substitute gx as some another variable u, simply write down here u, that is u squared du, that's it. Okay, so this is kind of easy substitution we have to find out the complicated problem. Now you know how to find the antiderivative u squared by using the basic formula, that is u3 over 3, right? But remember, there was no u in the original problem, but we let u as gx. What is gx actually? Gx was x squared plus 1. That means I'm telling you u is nothing but x squared plus 1. So once you have the answer, go back and replace u by the original variable. So this is the answer for the given problem. You see now, you use that pattern recognizing pattern technique and we found the answer. Okay, that's what they explained. Okay, this method can be applied only if you see some function time its derivative somewhere here. So this, 4.5 is simply explaining about those substitutions. So why don't you go through this 4.5 during this, 2 days, and you could start on working, you know, um, with that. So you use the guideline like this. Choose the substitution gx as u, then du by chain rule g prime dx, and you follow this. Okay. So I'm explaining with this easiest problem, the last explanation for today. Okay. Right. How do you find it?
The x cubed times 3x squared?
Yes.
Okay.
You see there easily, right? The derivative of x cube is what? If you keep gx as x cube, right? Then what is g prime?
3x squared.
3x squared. You see here? So if you keep, the first function as g function, then its derivative is right over here. If you see like this pattern, always you could use this technique. What is the technique? Technique says that, hey, keep u as that g. Then find the du. If u is x cube, what is du? Simply find the derivative of 3x cube, which is 3x squared, right? Simply I'm finding the derivative both sides with respect to x. If u is x cube, then what is du over dx? The derivative with respect to x, which is 3x squared, right? Then if you move dx to that side, that is simply you will get this. Du is 3x squared dx. What is my task here? My task is to change of variable. I'm going to change the original variable x to the new variable u, which is called the change of variable technique. Okay. This technique will make you easier to handle the problem. So whenever you see the function and its derivative near, use the u substitution. We call that as u substitution. There are plenty of examples given here. So why don't you go through and understand how they apply these change of variable techniques. So if this is the case, what I'm going to do is, yes, I could replace 3x squared plus 3x squared times dx is equals to du. So this is going to be du. But remember, according to my substitution, x cube was u. So this was u. That means what? That means I'm rewriting, given the original problem as u, right, times du by using new variable. Now problem is much simpler than the original, right? Now you could treat this problem as a new problem. Now go for the basic antiderivative formula. Only thing is instead of x letter, you have u letter. That's it, right? Then what is the antiderivative of u? The similar question I'm asking you, what is the antiderivative of similar to finding x, right? The antiderivative of x is x squared over 2. Right? In similar way, the antiderivative of u is u squared over 2 plus constant. But again, remember the original problem was in terms of x, so you had to go back and replace u by its original variable. My u was actually x cube, so I'm going and replacing u by x cube. U is x cube, but I have squared. So like this approach we use to find this kind of integration. So if you have like this complicated problem in antiderivative problems, so we use this technique. Okay, so make sure that you go through this. Remember, for coming test, we are going to cover up to 4.5.